of all, let me start by saying, I'm not going to tell you how to do optimal search with any inadmissible heuristic, just, some restricted class, but still more than admissible heuristics. So let's talk about admissibility and optimality. So we all know that a heuristic is admissible, right, if it gives us estimates that are a lower bound of the true goal distance, right, goal cost. For any state. So this is a state, and the red line is supposed to be the heuristic, like represents the distance of the estimate, and this is the goal. So this is an admissible heuristic. And we all know that A star with an admissible heuristic will give us an optimal solution, which is great. So is this a necessary condition? Well, we know the answer to that. The answer is no. So I'm going to propose a new definition. The definition is new, but it's been done before quite a while. So we call it globally admissible. So a heuristic is globally admissible if there exists some optimal solution rho, so this is the optimal solution rho, such that we get an admissible heuristic or an admissible estimate for any state along this path. But for states that are not along this path, we might get inadmissible estimates. All right? So we call this global admissibility, and we can argue about the name. We've done that before quite a lot. But let's say that for the question. So, I'm not the first to note this, right? So Pearl and Dexter did it many years ago. So A star with a globally admissible heuristic will guarantee that we find an optimal solution. Okay, and actually the same proof of optimality of A star works with a globally admissible heuristic. No changes. But sometimes heuristic estimates can be path dependent. Okay, so the landmarks, for example. So we're going to propose a slight modification of this definition of path dependent admissibility. So rho is some optimal path, and we're going to call a heuristic rho admissible. So a path dependent heuristic now. So it's rho admissible if for some optimal solution rho. And for any prefix of rho, we get an admissible estimate. Okay, so now we're evaluating this path, I, and because it's a prefix of our optimal solution rho, we needed to give it an admissible estimate. Now, if we have a different path to the same state, we no longer require the estimate to be admissible. Okay, and if it's some path that's not along this optimal solution, then we don't care about the heuristic estimate at all. So this is rho admissible for some optimal path rho, and we can generalize it to a set of optimal solutions, or a set of solutions in general. So if phi chi is the set of paths along which we have admissible estimates, if this is the set of all optimal solutions, we're going to call H path admissible. So it basically means that for any prefix of any optimal solution, we're going to get an admissible estimate. And if it contains at least one optimal solution, we're going to call it globally path admissible. So there are some examples of globally admissible and globally path admissible heuristics, or they haven't been viewed as heuristics, but we can view them as heuristics. So basically pruning methods and partial order reduction methods can be seen as a heuristic that assign infinity to the states they prove. And they're going to be globally admissible or globally path admissible depending on what information you need. But what I'm going to show you here is actually something that does more than pruning. So we'll see that soon. Alright, so when we have a globally path admissible heuristic, A star does not guarantee optimality anymore. Okay? Tree-based search will guarantee optimality, so for example, ID A star will work. With A star, we need to make a bit of changes, which I will discuss later. So this is like our goal in this talk, okay, to find some globally path admissible heuristic. And what I'm going to show you is a path admissible heuristic for strips. Okay? So first of all, I'm assuming you all know strips, right? You've been here long enough. This heuristic is based on what I like to call a chicken logic, which is basically why did the chicken cross the road to get to the other side. So how do we get a heuristic out of that? Well, every action along an optimal plan is there for a reason. Okay? So it either is there because it achieves some goal, or it's there because it achieves a precondition for another action. And then that other action has to be there for a reason. And we're just going to assume that we have an end action, and then it's basically just achieve a precondition for another action is the only case we have. Alright, so let's look at an example. So this is a logistics example. So we've got two locations A and B, two trucks, T1 and T2, and some package O and A that needs to get to B. And then what we did was load the package onto truck 1. Okay? So we know that there must be a reason for applying that action. Okay? Or more formally, if this action is the beginning of an optimal solution, then there will be some action that needs it. So the only effect of load the package into truck 1 is that the package is in truck 1. So that means that any optimal continuation of this path, okay, any continuation of this path into an optimal plan will have some action which requires that O is in T1. Okay, so it will have some action which is preconditioned on this. So the basic idea is the idea of intended effects, and that's actually related to what Christian Ruth was discussing in the last session with the relevant part. Okay? But the intended effects is not just what's relevant for one path, but what's relevant for all the paths, so all possible continuations. So a set of propositions X, which is a part of the state reached by pi, okay? It's an intended effect of path pi. So this is a bit informal. If we can use X to continue pi into an optimal plan. So basically, using the notion of relevant, X is the part that's relevant for pi. Okay. So we formalize this using causal links. So by using X, we mean that there's a causal link between pi and the continuation that consumes something in X. I'll show that later. So first of all, causal link, just in case somebody missed that last 3 times we had it at this conference. So if pi is some path, then the triple AIP AJ, so here actually this is a proposition, is a causal link. If AI achieves P, AJ is preconditioned on P, and there's nothing that interferes with P in between them. So nothing added links P between AI and AJ. So now we come to the formal definition of intended effects. I might lose some of you here. I know it's a complicated definition, but I will wake you up in a few slides. So the definition is with regards to a set of optimal solutions, opt, okay, and unfortunately we need that. So given some path pi, a set of propositions X is an opt intended effect of pi, okay? If there is some continuation of pi, that we're going to call pi prime, such that pi prime is an opt, okay? So this is one of our optimal solutions. And pi prime consumes X. So basically pi produces X and pi prime consumes X, and exactly X, okay? So nothing more than X. So the exact definition uses causal links. So if the opt is the set of all optimal plans, we're just going to call it the intended effects of pi, and otherwise we're going to have intended effects of pi with regards to opt. Alright, so in the example we had before, the intended effects of load O T1 is a set containing a singleton of O in T1. But for more complicated example, we can get something kind of weird. Basically it's a set of sets. Okay? So working with the set of sets is not very nice. We don't like it. But we can have a logical interpretation of that. So we can interpret the intended effects of pi with regards to opt as a Boolean formula. Okay, so every set of propositions that's an intended effect is basically a truthful assignment to the formula. And we can interpret any continuation of pi, okay, any path that continues after pi, as also as an assignment, okay, or Boolean evaluation. So it assigns true to the propositions that it consumes from pi and false to the propositions that it doesn't consume. All right, so again, the notion of causality. And then we can basically say that some continuation pi prime satisfies our formula for describing the intended effects phi. All right. So in this example, now it looks much simpler, right? So the formula that captures the intended effects of load OT1 is basically O in T1. And what that means is that in any optimal continuation of this prefix, there must be an action which consumes something in this. Okay. All right. So this is the theorem that says that basically the landmark or the formula must be obeyed or must be used. Hey, we have a mic now. All right. I'm halfway through. Okay. So basically it says that if we have a formula for describing the intended effects of pi, any continuation will satisfy the formula. Okay, so that's kind of obvious. So unfortunately, and if you have any intuition with landmarks, it's p-spaced hard to find the intended effects. So the good news is we can approximate them, or rather, if we have an approximation, we can use it. So if we have a superset of the intended effects, then it will still give us a valid constraint. Okay, so we can still use that. So what I'm going to show you now is one possible technique for approximating the intended effects. And if I asked you before, with all the sets and definitions, you can now wake up, because now we're getting to the intuition part. So the intuition here is very simple. The set of propositions X cannot be an intended effect of pi if there is a cheaper way to achieve X. All right? So if we have a path pi and it achieves something, then X, so some part of what it achieves cannot be an intended effect of pi if I can achieve only that part cheaper. So before I get to this more formal definition, so let's think of this. So path pi achieves A and B, all right? So assume pi has a cost of 5. If I can achieve A with a cost of 4, then that means that A cannot be an intended effect of pi. So that means I'm going to need to use B as well. I might need A as well, okay, but I'm also going to need B. Otherwise, pi will not be the beginning of an optimal plan. So this is the intuition I want you to keep in mind. All right, so assume we have some library of shortcuts paths. Then X cannot be an intended effect of pi if we have some shortcut in our library that's cheaper than pi and achieves X. All right, so that's the intuition I was just telling you about. So let's look at this example, and I'm also going to show you what we call the causal structure. Okay, this is nothing new. It's basically the actions and their causal links. So we have these two tracks here, T1 and T2, and they're starting at A. And then track 1 drives from A to B. And then track 2 drives from A to B. And then track 1 goes from B to C, and from C to A. So you can see the causal structure here. So drive T1 AB supports drive T1 BC, and that supports drive T1 CA. And we also have drive T2 AB. So this is our path pi. And this is a shortcut, okay, drive T2 AB, which reaches the same state. So if I have a shortcut that reaches the same state exactly, then I know I can prune pi. But if I have something that achieves part of what pi achieves, then I can use that in a more, or well, in a heuristic. So I'll show you how. All right, so we like logic. Okay, it's much better than working with sets. So assume we have this library L, and we have a path pi. So we can express our approximation of the intended effects by a CNF formula. So for any path, for path pi and for any path in our shortcut library pi prime, which is cheaper than pi, basically what this means is that I need to use some proposition that pi achieved and pi prime did not. Okay, so for each path in the shortcut library, I have a clause which says that I need to use one thing, at least one thing that pi achieved and pi prime did not. And if pi and pi prime reach the same state, then I basically have an empty clause, and I know it's a unsatisfiable formula, and I can prune the state. All right. So I have this formula, and I can interpret it as basically an existential optimal landmark. So it's not a regular landmark, okay? It doesn't have to be satisfied by any plan, but we know that there is at least one optimal plan which must satisfy this, okay? So this is why we call this an existential optimal disjunctive action landmark. So the actions that have preconditions that satisfy this are the disjunctive action landmark. All right. So one thing I have to tell you is how we get our shortcut library. So the first observation is that sorry, it doesn't have to be static, okay? I can generate it on the fly for every state, for every path, actually, that I evaluate. So what we do is we look at the causal structure, which I showed you before, and we basically try to remove parts of the causal structure and to create a shortcut, okay? So if you look at this example, by removing this chain, I get the shortcut. Right, so I will not go into the exact details of what we do with the causal structure. We have some cases that we try to find, and you can read the paper if you want. All right, so as I said, the formula we get describes an existential optimal landmark, and we can actually use that along with the regular landmarks heuristic, or the admissible landmarks heuristic, and do a cost partitioning over all of them together, okay? So we can write the LP and solve it and get a path admissible heuristic, okay? So as I said, A star will not guarantee optimality with that heuristic because it's not admissible, it's path admissible, or it's actually opt path admissible, okay? When opt is the set of opt intended effects that we use. So what we need to do is basically, so if opt is the set of all optimal plans, what we need to do is modify A star to reevaluate a state, the heuristic value of a state, every time we find a cheaper path to it, okay? So if we reach some state via a suboptimal path first, then our heuristic is not going to be guaranteed to be admissible. So we need to reevaluate. All right, so we also have, so what I discussed so far was path admissible. We also have a version that's row admissible for the lexicographically lowest optimal plan. And that requires a bit more modifications to A star. I will not get into that. So let me just quickly show you the results. It does better. So actually, what's surprising, or what might be surprising, is that the version that uses the row path admissible heuristic, so for a single path, is not better. So technically, it's a more informed heuristic, but it doesn't do better because the search needs to be modified, you know, in a much more strict manner. And if you look at the number of expansions, it also does better. And that's it. Thank you.
Thank you. Interesting talk. So I didn't get that thing about A star is not optimal with the path admissible. Yeah, it seems to me that if it is path admissible, there exists an optimal path, right? That for every prefix of the path, the value is less than or equal to the H star of the node in that path. So that will guarantee you that the prefix of that optimal path is always in the open list. So you cannot expand the goal before expanding that prefix. So that prefix will continue to be in the open list, and eventually you will find an optimal path.
So I got another one. So the thing is that you can construct some examples with ridiculous heuristics, okay? So we can build a graph. Actually, Malte did that as a counterexample in my defense. So you can construct a graph with some heuristic values so that some state is reached first via some suboptimal path, and if that's the case, a path admissible heuristic might prune that state. And then you're not guaranteed to find an optimal solution. All right, so you need to ensure that your estimates along the optimal path use the optimal way to get there.
So I was just interested in your library. Do you generate it on the fly, or do you generate it beforehand?
Yeah, so what I do is I take the causal structure and just try to take some parts of it off and see if I get, a valid plan, and what that reaches I use as a shortcut.
Right, so it's just pre-processing before any problem.
So actually I do that for every state I evaluate. So every path has a different causal structure, and so it's a lot of work for each evaluation.
Yeah. Okay.
There's room for improvement there.
There's a lot of room for improvement. The shortcut library that Aerosys uses is a lazy shortcut library in the non-informal sense of this word. And there's a lot of things that can be done there. But the critical part is not to pay too much because it is online.
Right.
So that's the tricky part.
So maybe this is a crazy question. Could you learn enough of these pruning rules that you could learn how to do TL plan online or something?
So I doubt we can get to the level of TL plans control rules, but so I'm working on learning these shortcuts online, and so we do learn them, but then you pay a lot more for each evaluation. So we're not at a point where it's actually worth it yet, but hopefully with some more work.
All right, thank you, Patrick, and thanks everyone for sticking it out to the last session of the last day, or next to last session. I'm Jordan, as Patrick mentioned, and I'm going to be presenting work that I did with my co-authors Ronnie Stern and Ariel Feldner from the Ben Gurion University of the Negev in Beersheba, and also with Wheeler Rummel, my former advisor at the University of New Hampshire. So to start off, I'd sort of like to motivate the area of bounded cost search. I think we all understand very well that optimal searches like A*, they provide us with optimal cost solutions, but they don't scale super well. Conversely, greedy search finds solutions quickly, but at the cost of finding expensive solutions. So that's what we're looking at here. We've got a grid pathfinding problem. On the x-axis, we're looking at the size of that problem. And in the left plot on the y-axis, we're looking at the number of nodes generated during solving, which is an analog for time. And on the y-axis in the right-hand plot, we're looking at the final cost of the solution relative to that of A*. So you can see A* starts taking lots of time very quickly, but greedy search scales well. On the other hand, A* is always optimal, and greedy search starts to cost a lot. So that's why we have bounded suboptimal search algorithms of the sort that I'm always bagging on about. Weighted A* is shown here. That's the one people are most familiar with. So the idea of bounded suboptimal search is that we can sacrifice some limited amount of optimality in order to get fast solving times without incurring huge overhead in terms of the solution eventually found. Unfortunately, bounded suboptimal search isn't appropriate for all possible settings. So let's imagine, for example, that I have some budget. I have $20 to get home. From a large problem like getting home from Sao Paulo, that's not going to work. But from Boston, I might be able to swing it. So that's sort of what's shown here. We have this thick purple line. That would be a suboptimality bound, the standard W that you supply to weighted A*. And it's at a fixed place in this plot. So the suboptimality bound doesn't change as problem size increases. But unfortunately, a budget has this weird relationship to problem size. As problem size grows, generally the cost of the solutions also change. And that's why we need bounded cost search algorithms, because they fill a niche that isn't currently satisfied by bounded suboptimal search. So that was the motivation for the problem that I'm trying to solve. And in the rest of the talk, I'm going to talk about a previous approach to bounded cost search, potential search, presented last year in Freiburg at ICAPS. And I'll point out some problems with that approach. And then I'll talk about our new algorithm, bounded cost explicit estimation search, or BEES. And time permitting, I'll talk about some bigger picture issues that BEES raises and a couple of other algorithms that were in the paper but aren't really the focus of this talk. So for those of you who weren't there or don't recall, potential search is a search in, it's a best first search on nodes in order of the likelihood that they will satisfy some cost bound C. So we try to expand nodes roughly in the order of how likely it is that a solution exists beneath them of cost no more than C. More directly, it's the probability that the cost of arriving at the node plus the optimal cost of completing a path through that node is less than C. And immediately we may all notice a problem, which is, man, that's going to be hard to compute. So there are situations, for example, if h of n is related to h star of n in a linear manner, where we can compute other evaluation functions, like the linear relative error model shown here, which will produce an equivalent order. So we can search on something we can actually compute, so long as we know something about the relationship of the heuristic to truth a priori. So what's happening here is C is our budget, G of n is the cost already incurred, and H of n is our estimate of cost to go. So it's like, how much do I have left to spend? How much could I possibly spend and still get a solution? And how much do I think I'll have to spend? So that's why that ends up working. Unfortunately, potential search doesn't always work very well. And that's what we're looking at here. In particular, it doesn't tend to work well if actions have cost. So what we're looking at is the performance of two bounded cost search algorithms on this inverse cost tile puzzle. So it's just your standard sliding tile puzzle, but the cost of moving a tile has been changed to introduce action costs. On the x-axis, we have the cost bound C with which the algorithm was run. And on the y-axis, we're looking at the total raw CPU time on a log scale. So the red line is potential search, and this green dotted line is speedy search with a cutoff. So it's a pretty simple baseline. You run greedy search on the number of actions you estimate exist within a plan, and then if you ever incur cost greater than C, you just prune that away because it can't lead to a solution. And so initially, both algorithms have similar performance. This is the area of the problem in which no solutions exist. And then as we get to the part of the problem where we can find a solution within our cost bound, potential search sort of trails off up here, focusing on the cost to go, as I'll explain in a moment, whereas greedy search starts to be able to find solutions and short solutions. So it goes quite quickly. You're looking at something like a 3 orders of magnitude difference between potential search and this baseline. So to understand why there's such a large difference between those problems, I've constructed this very simple example. It's a navigation problem from the node S, the start state, to node G, a goal state. And there are 2 possible paths through this graph, one through A and one through T. I've written the relevant heuristic information about the node here. So you can see that the path through A is very cheap. It's going to cost 7. So 1 incurred, 6 to go. But it's got 6 steps. Conversely, the path through T is expensive, but it's got 1 step left. And my budget is such that I will admit T as a possible solution. Unfortunately, the linear relative error model and potential search don't pay attention to the length of solutions that we could get to. And that's what's going to cause our problem. Because we don't take D into account, we prefer A to T. And in situations where the path through A is acceptable, if I want a solution quickly, where the path through T is acceptable, if I want a solution quickly, I need to go through here. So BEES, or bounded cost explicit estimation search, corrects this. The two things that it's really trying to fix for is we want to move away from these error models because we may not know that about a problem a priori. And we want to get better performance on domains with action costs without sacrificing performance on unit cost domains where potential search was already pretty good. So the way we're going to get there is we're going to estimate which nodes are within the bound. So we're not going to rank them on probabilities, we're just going to make a binary decision. Are you in or are you out? And then of those nodes that we think are within the bound, we're going to search on those in order of estimated number of actions remaining. So I call that set of nodes that we estimate to be within the bound the focal list. If you're familiar with A star epsilon, you'll have heard of this term before. But don't confuse it with the focal list of A star epsilon. These are simply the nodes we want to focus on in search. They're probably on promising paths, so we're going to look at them more closely. One way we could define the focal list is we could use the admissible heuristic, and we could construct this this lower bound on the cost of a solution through a node, F. So cost of reaching, cost to go. And we could look at all nodes where f of n is less than or equal to c, because those are exactly the nodes that could in any potential world lead to a solution. But the focal list is supposed to focus our search into the promising regions, so we're not going to use admissible heuristics. We're going to use h hat, some inadmissible best effort guess of cost to go. Maybe it's too high, maybe it's admissible sometimes. It doesn't matter so long as it focuses our search into reasonable places. So we construct this inadmissible doppelganger of f called f hat, and what it really is it's our best guess of a cost through node n. So if we build our focal list in this way, it's those nodes which they probably lead to a solution. This raises another problem, which is we may be in a situation where our list of nodes that probably leads to a solution is empty, but our list of nodes that could lead to a solution still contains members. And we need to prove that no solution exists if we think no solution exists. So the reason that can occur is it is often the case, or at least it should be the case, that f hat of n is at least as large as f of n because it's your best effort guess. And if your admissible heuristic is higher, you should just use that because it's admissible. So it can be the case that our focal list, those nodes where we think lead to solutions within the bound, is empty. But our open list, those candidates that still have to be expanded to show that no solution exists, contains elements. In which case we want to use A star to enumerate those, or to expand those nodes so that we can show no solution exists to our problem. Or alternatively, maybe we'll get some new nodes on focal because our inadmissible heuristic was too aggressive. So we have to modify what we were going to do in B's just a little bit. We're going to estimate which nodes are within the bound. And if we have some of those, we're going to search on them in terms of actions to go. And if we don't, then we'll use A star search to prove that no solution exists. So B's ends up being a best first search on this function, the select node function. So if focal is empty, return the node with minimal cost or minimal estimated actions to go. Otherwise, return the node with minimal f on open. If we go back to our simple graph example here, what's going to happen is, so long as our inadmissible heuristic is accurate, it will predict that T exists within a cost bound of 20, and it will predict that A exists within a cost bound of 20. But 1 is less than 6. So we're going to follow T instead of A. So to go back to the inverse cost tiles puzzle example, again, remember the cost bound C that we provide to the algorithm is on the x-axis, solving time on the log scales on the y-axis. You can see that initially all of the algorithms are pretty much the same because there aren't any solutions within the bound and there aren't many nodes that we have to evaluate to prove that. But as we reach this, this middle point here where things start to be solvable, you see that B's is slightly better than the baseline and both are better than potential search. And as we go out here in the area where many solutions exist because the bound is quite generous, the algorithms are comparable with speedy with the cutoff slightly edging us out. And that's because we're sitting down and thinking, is this good enough? Is this not good enough? I'm going to evaluate a couple of heuristics to see one way or another and maintain several orderings over the nodes to keep track of that. And speedy search with the cutoff is just able to rip through many more nodes than we can because we're deliberating. In a moment, we'll see that that deliberation, in fact, often pays off. You remember that our second goal for bounded cost search, or for Bs rather, was that we not sacrifice performance on unit cost domains. Indeed, we don't. So this is the same set of tiles puzzles, but now we've gone back to the normal action cost where it's just 1 to move any given tile. And you can see that the performance of the 3 algorithms is very similar here. But that easy, hard, easy transition still exists where you have cost bounds that are too low, then cost bounds that permit only the optimal solution, then generous ones. The reason that I propose Bs instead of this baseline is that the simple approach doesn't always work, unfortunately, or perhaps fortunately for me. So in domains like this doc robot one, where this is taken from the planning textbook of now Traverso and Galab. So again, cost bound and time. You can see that initially where nothing is solvable, everyone does about the same. But as we reach the critical point where some of the problems become solvable, the speedy search doesn't work as well anymore because you actually, pardon, you actually have to get, you can't just follow the distance to go heuristic because there's such a misalignment between it and f hat in this particular case. So you have to take the, you have to narrow down the set of potential solutions by looking at that inadmissible information, or you're just going to end up in some very horrible part of the space forever and not solve anything, even though solutions exist in your cost bound. So to summarize the technique, or to summarize the talk a little bit, Bs outperforms the previous state-of-the-art in bounded cost search by a couple of orders of magnitude in some domains. It's also better than the simple baseline in that it's far more robust where the problems are difficult to solve. And the way it gets there is really the interesting thing. When action costs are different, it takes advantage of D, and that's why it's so much faster. When inadmissible heuristics are present, we use those to guide the search. And then we use admissible heuristics to prove something about the space afterwards, which, you know, we're relying on this fact here that finding solutions and making proofs about the problem that no solution exists or that we're within our suboptimality bound or whatever you want are different. And, you know, this is the sort of thing that I find myself saying over and over again. You know, the reason that techniques like explicit estimation search, that optimistic search work is because there's such a large gulf between the bound that you place on a solver and the solution that it actually returns, and paying attention to the fact that, hey, finding the solution and proving something about the space are very different leads to what would be, compared to traditional algorithms, considered weird search orders, but that are very effective search orders. The idea that using inadmissible heuristics is good is not, you know, foreign to the planning community, but in the rest of heuristic search, it isn't taken to heart as often, which is what we're seeing here. It's a comparison of the optimistic search algorithm, which runs weighted A star with a high weight, to skeptical search, which runs weighted A star with an inadmissible heuristic. And you can see that, hey, using the inadmissible heuristic, we dominate the thing that only relies on the admissible heuristics. And that's, you know, not just doc robots, that's also a common phenomenon. Similarly, greedy search on H versus greedy search on D, using these distance to go estimates often leads to large improvements in terms of solving time at the cost of solution cost. So you may find something much faster, as we see here, 4 orders of magnitude faster, in fact, but the cost of that solution, or the quality of that solution, in this case according to the IPC metric, is much lower than the quality of the greedy solution. Thank you.
Do you assume some sort of linear relation between H and H star, and is there a reason for that? Have you tried some other relations?
So that's what potential search did. or at least with the linear relative error model. In our case, we don't. So I didn't say where these inadmissible heuristics come from, but so in the case of planning, they're provided. In the other domains, we use the technique we presented at ICAPS last year to learn them online from a relationship between parent and child. So H should go down, or F should stay constant, but it often goes up. So that's a noisy sensor, and you learn from it.
I want to know if I should implement that in Llama, for example, to speed up this planner, or if you intend that to do, or to compare with existing planners. Is that on your research agenda?
So in the paper, we have results that compare bounded cost search algorithms across the fast downward planner. So we implemented these in the fast downward code base. So Llama is a purely unbounded algorithm. So it wouldn't be totally unlike this greedy search with bounded cost cutoff. And I suspect that won't work super well for some domains, but could be competitive if the cost bound is very generous. But I haven't compared with Llama directly.
Let's see, maybe I can follow up on Stefan's questions. So you could run this in an anytime framework. So just, use -1 from the previous cost bound on the next. So have you looked at sort of what's the anytime profile of it?
So it turns out that, at least as far as bees is concerned, it doesn't work super well in an anytime framework. And the reason for that, so we did try that because we got some comments on another paper from a reviewer saying, hey, this looks like it could work in an anytime setting. And the reason for that is that we're very sensitive to this prediction of whether or not we're within the bound. And for a one-shot thing, it can work well. For multiple shots, we end up eventually just running A-star, and that's not super efficient. Like A-star has a very bad anytime profile. So by using relative bounds, we're less sensitive to inaccuracies in the inadmissible heuristic because we're just saying relative things. So that ends up working better, especially where H hat is not incredibly accurate. Yeah.
Well, okay. So I don't know if you saw a talk in the other room earlier session, which was solving resource-constrained shortest path, which struck me as a somewhat similar problem. You have a double objective or two objectives, and you have a budget on one of them, and you want to optimize the other one. So
yeah,
here you're optimizing time, but you could just as well optimize something else, right?
So Hutan's paper, yeah. So we could definitely supply the hard constraint as C and then take an anytime approach after that point, right? So we could just exhaust all of the solutions within C slowly and use the alternative ordering instead of D, order on whatever your second criteria was. I have no idea how well that would work. But it might make sense to sort of do B's again beneath that, right? So you have the focal list on the hard constraint, but then you build a focal list on the soft constraint and search on that in terms of time, or in terms of actions remaining. I can imagine that working quite well, but I haven't looked at it.
Okay, so this is the final question, even though we actually have plenty of time. So you mentioned that you're kind of sensitive to the inadmissible estimate being accurate, and that's like accurate in an absolute sense. It actually estimates the cost. So I was wondering if you have something that is not accurate in the absolute sense, but accurate in a relative sense, that for children of the same parent node, it sort of picks. If it says that this child has a lower cost than that child, then chances are this child actually has a lower cost to complete, just not anywhere near what the actual value of the heuristic is predicting. Could you make use of that type of information?
It's unclear how we would do that. There's almost certainly some way to get it done, but because of how we define the focal list, right, we define it in or out. So we're sensitive to consistent we're sensitive to consistent overestimation. So if you always say it costs 50 when it costs 40, and our bound lies in that region, then we're up a tree. If you had accurate relative information, then maybe you could define that list as accurate relative to minimum F, and then use that to try and find the cost bound from there. Because you could compute W such that it would only permit things within your presumed bound at that point. But I have no idea how well that works. For EES, it doesn't work well, for example. So we tried something like that, setting EES with various weights across multiple runs instead of designing a bounded cost algorithm directly. And it turns out that that dog won't hunt usually.
Well, I've run out of questions.
Hello, hello.
So, last speaker is Eric,
Yeah.
and he will be talking about predicting optimal solution cost.
Yeah. Hello, everyone. First off, I'm very happy to be here to present part of my what's going to be my dissertation, my PhD dissertation, and I'm going to present to you an algorithm to efficiently predict the optimal solution cost. And this is joint work with Ronnie Stan, Ariel Fellner, and my supervisors, Zandra Tillis and Rob Holty. So the problem definition here is very simple. We have a start state, we have a goal state, and of a state space problem, and then we want to predict the optimal solution cost. The definition is fairly simple. The question is, why do we want to do that? So sometimes when you have a planning problem, the entire plan is not needed. All you need is just like an estimate of the optimal solution cost. That might be enough for you to tackle the problem. For instance, say Patrick has a construction company, and during the bidding process, he doesn't need to know the entire path to solve the project he's bidding for. So all he needs to know is a very accurate of the optimal solution cost. So that's why we're interested in building this kind of system. Also, we could use this sort of predictions or estimations to enhance search. So last year, we presented at SOX how we could use, for instance, this kind of algorithm to find a W value for weighted A star or weighted IDA star, so we can find near optimal solutions very quickly. Also, we played with the potential search algorithm that Jordan briefly mentioned here, in which we find an upper bound on the optimal solution cost, and then we just run the potential search algorithm. So also this year we're going to have a short paper at SOX in which we're going to use exactly the algorithm I'm presenting here today to learn heuristics. So if you're interested in learning heuristics, maybe you want to take a look at that short paper. Only 2 pages, very easy to read, lots of empirical results. Maybe one visit to the washroom is enough to understand. Okay, so by now you might be wondering, so what is the difference of this kind of predictions with heuristic functions? Because that's essentially what a heuristic function is doing, right? You're estimating the optimal solution cost. So, but we all know that very often you have admissible heuristics, and those they're gonna underestimate the optimal solution cost, and this is gonna imply in very poor estimates of the optimal solution cost. And also, heuristic functions, they better be fast because you want to use them to guide search, and we're interested in getting very accurate predictions, which is in contrast with guiding search. So we can be a little bit slower. We don't want our prediction methods to be as fast as a heuristic function, but we want it to be accurate. So we also, we're going to measure our system based on the accuracy of the estimations. Whenever you build a heuristic function, you're probably going to plug in in a search algorithm, and you want to show that you find solutions quicker. So here we're just interested in make accurate predictions of the optimal solution cost. So I'm aware of one algorithm for doing that, and that's the one we presented last year at SOX. This is joint work with Ronnie and Shahab. And the problem we have with that algorithm is that, is it working? Okay. Is that if we want to apply for larger state spaces, sometimes it doesn't scale very well, as we're going to see in the empirical results. So, okay, let's move for a definition. This is a fairly simple definition, but it's also very important. So I want everybody to pay attention, and there is a nice picture here that I want you to remember, because you're going to need that to understand the algorithm. So here we come. That's the picture I want you to remember. We define as a type system as a function that's going to get a state in the original state space. You can see here the original state space. This is much larger than what we call the type system space. And the type system is actually going to be a function that gets one state over here and maps to a type in the type system space. And what the type system is doing is just making a partition of the state space. It's just breaking the states into types. If it helps for you to think of this as an abstraction, that's fine for now, but there are differences. And if you want to learn more about it, I'll be happy to talk to you offline. I can explain the difference between type systems and abstractions. Okay. Please remember of this picture. And to make sure you understand, I'm going to go through an example. So the type system I'm going to give here is an example. It's going to consider a heuristic value, a heuristic function, and also some other information about the problem. And in search, we like slide tile puzzle, so I'm going to use the little 3x3 slide tile puzzle as an example. So right there you have the goal state for the slide tile puzzle. If you're not familiar with it, you could get this tile and move over here, or get this tile, move over here. And I can give you any configuration of the puzzle, and the goal is to get to that configuration over there. And the heuristic function we're going to use is just the distance from the blank to its goal position. So let's suppose if the blank is over here, then we need 2 moves to get it over here. That's the goal position. And that's going to be our heuristic function. And the other information we're going to use is the position of the blank in the puzzle. So the blank could be in a corner, on the edge, and also in the middle. So again, this is just a toy example so you can understand the concept of type systems. We don't use this in practice at all. It's just small enough so I can put in a projection. So here's how it looks like the type system space. So if you get all the possible states you have in the 3x3 slide tile puzzle, they're going to be projected in this type system space. So in this case here, the heuristic is going to be 0 because the blank is already in the goal position and the blank is in the corner. So that's what it's saying, this type over here. If you go, for instance, for this other one here, then the blank is in the edge and you have 3 different moves to get to the goal. So these 2 values, like the heuristic and the position of the blank, that's going to give you the type system. Great. So now we can move on, and I'm going to start presenting the algorithm we propose in this paper. But before that, I would like to talk about another method. That's something we tried, and we're hopeful that would work, and we didn't get very good results. And that's an algorithm called stratified sampling. So it's a fairly old method from '89 by Chen. And Chen designed this algorithm, stratified sampling, I'm going to call here SS, to estimate the size of search trees. And it goes like this. So you have the start state, and you want to estimate the size of the search tree that you're going to have rooted on that start state. So all we're going to do here is we're going to expand all the children. And let's say we have these 3 children. And we're also using a type system. And the type system here is going to give us colors. So I'm going to give a state to the type system, and the type system, hey, here's a color back. So if you ask that for the type system, we have nodes that are red, and we have one node that is blue. And the assumption that Chen makes here is that nodes of the same color, they're going to root subtrees of the same size. So what's going on here is that the type system told us that this node is red and this is also red. So we're going to expect that whatever we see below this node is going to be of the same size, the same number of nodes we're going to see below this node. So the way Chen thought of this was that, okay, if we know this information, we can just explore one of the two nodes and ignore the other one. So we're going to get just one node of each type at each level and expand it and explore it further. So let's say we get the right one and we get this. So we saw two nodes over there, and then we're going to assume that on the other side, so here we have two nodes, we're going to assume that we also have two nodes over here. And if you're happy enough to get this result, then we're able to estimate the size of the search tree without actually exploring the entire search tree. So that's using the type system trick that you can make this process efficient. Okay? So can we use this to predict the optimal solution cost? What I find very interesting about this algorithm is that you could use it to measure any kind of numerical property of a search tree. In Chen's case, you were measuring the size of a search tree, but you could think of any other measure you wanna see in a search tree and use this algorithm as well. So I was wondering, maybe we can use this to predict the optimal solution cost. And we gave it a try. And the way we're going to do it here is that we're going to run this algorithm until we find the goal. And remember that at every level of search, we're just going to get one node of each type and we're going to explore it. And what happens here is it's that, well, you actually have to find the goal, and it's very likely that you're going to find the goal with a very suboptimal solution. And in some experiments we run with the 24 puzzle, then we get like twice as long solutions compared to the optimal solution cost. And if you get, for instance, Manhattan distance, that's a very simple heuristic for the problem. If you measure like the accuracy, Manhattan distance is actually better than this method. So we wanted something better. And then we came up with the bidirectional version of the SS algorithm. And the idea here is that we're going to have the start and the goal state, and we're going to apply SS from both ends at the same time, and we're going to alternate it. So let's say we start from the start state and we expand all its children. And here the black dots, they're actually the states that SS is going to expand. And the white ones are the ones that is just, you know, I don't want to look at it because I had another state of the same type. And then as soon as we do this in one direction, we move for the other direction and we move one entire level. And then we move back to the forward search, and then to the backward search, forward search, backward search. And then the thing here is, okay, when are we going to stop, right? That's the big question. So the assumption we're making is that if you have two nodes of the same type, let's say A and B are of the same type, this is giving us some information that the two frontiers are somehow close in the state space. However, if we just use this as a criteria for stop searching, it's going to happen that we're going to underestimate a lot the optimal solution cost, because the type system is making this compression in the state space, and then even though A and B were still somehow far from each other, they were of the same type. So we need something smarter here. And this is what we came up with. So now I'm changing the notation a little bit. Before I just had like the little dots, and now we have these boxes. And what the boxes mean is that so here we started with the start state, and we made a bunch of steps with the bidirectional SS, and we got to some level in which we saw a state that was of type T0. So we could have more stuff on that level, but I want to highlight here that we had a state of type T0. And let's say we made a bunch of steps from the backward search as well, and then at some point we also found a state of type T0. But we're not going to stop there. We're going to keep advancing the forward search to see if that's going to match with other layers in the backward search as well. So we had a first match over there. Okay, we have two states of the same type. That's good. We might be close to each other. But as soon as we expand another layer and we see another state, and now it could be a different type, could be another T0 as well. And okay, they're the same type, so now we have a stronger clue that, okay, they might be closer to each other. And we keep doing this for some levels, and that's going to be input parameters for the algorithm. And as soon as we have a match for a given number of layers, then, okay, this is going to be our prediction. We're just going to sum up the number of steps we have up to here, plus the number of steps we had up to here. And that's going to be the prediction of the optimal solution cost. So this process, that's what we call one probe of the algorithm. If you repeat it like many times, we're going to be learning more about the state space, right? Is this working? So if we do a bunch of probes, we're going to learn more. And if we do like a very careful bookkeeping, we can actually get an interesting result that says that, this is very informal, but in the limit, as the number of probes goes to infinity, you're guaranteed to get the optimal solution. And it's pretty straightforward. Actually, it might not be here right now, but if you check the paper, this is a very, very straightforward result. Okay? So let's... that was an interesting result, but we're never going to get there in practice, right? You have to push the number of probes to infinity, and we're never going to see that happening. So then we evaluated the method in some standard heuristic search domains. And we're going to be comparing here our method, the bidirectional SS or BIS, with SCP, that's our method from last year. And we're also going to throw some heuristic functions in there. And we're going to see how they compare to each other. So this is actually the worst result we had. It's on the 15 puzzle. We're comparing our bidirectional search with SCP and also to Bootstrap, which is a inadmissible heuristic function. And here, what I'm showing is the error. So 0 is good, and higher numbers are bad. And we're dividing for solutions with different solution costs. And what we can see here is that SCP is doing better than our method, which is pretty much the same as the inadmissible heuristic. So what happens here is that we have this set of parameters, like the number of probes you're going to use, and also the number of layers that you're going to use to make the prediction. And we fixed the same set of parameters for all the experiments we had. And the way it is here, this set of parameters just they don't seem to be like a good set of parameters. But if we allow more time for the algorithm to find a better solution, then we can actually get results just like SCP. But if you move for the blocks world, let's say you have 15 blocks, and then we make almost perfect predictions over here across problems with different solution costs. If we scale up for 20 blocks, then SCP doesn't scale very well actually, and that's why you don't see it here. And we still make almost perfect predictions anyways, so that's quite interesting. If we go for the 24 puzzle, then again you have, say, solutions with 100 moves, and the error is like 0.03, meaning it's like 3 moves longer or 3 moves shorter than the 100 moves. So that's very, very accurate. But we wanted to test if this would scale even further. So we wanted to try in much larger domains. But the problem we have here with trying with larger domains is that we actually have to find the optimal solution for those large domains, right? We did it anyways with this light tile puzzle, and we derived a way of measuring how good the predictions are. And the way we did was, in 95, I guess, there is a paper by Parberry in which he proved that there is a lower bound and upper bound on the average optimal solution cost for these light tile puzzles that is cubic. So then if you have a lower bound that's cubic, upper bound that's also cubic, we're just going to fit some cubic function in between using the values of the light tile puzzle we knew, right? So here are the results. We have the 6x6 light tile puzzle, 7x7, 8x8. We have here the time in minutes that it took to make the predictions. The polynomial fit for the 6x6 said the average optimal solution cost is going to be 171, and this is very close. This is also very close. We were amazed to see, even though we're not sure this is actually the average optimal solution cost, but we had like these two different methods, and they agree quite a lot. So that was interesting. Okay, as conclusions, so we presented this algorithm BIS, which is capable of making predictions for very large state spaces and very efficiently as well. And SCP also does this kind of predictions, not for large domains. Actually, I have it over here. And the problem is, for BIS, we might need to have a goal state so that we can do this reasoning backwards. There might be other ways we could play it and make sure that we could apply this method when we don't have the fixed goal state, but we still have to investigate it. And it's the same with the invertible operators, because we have to do this reasoning backwards from the goal somehow. And the way we're doing here is that we're just assuming we have the invertible operators, but there might be another way of doing it. And yeah, I guess I'm ready to take questions if you have some. Yep.
Thanks, Levy. So you sort of hinted earlier on that it's not useful as a heuristic function for guiding search, but I don't follow why you couldn't, for example, just write down your type values, right? Can't you just back up the goal node you find through your tree, and for all type values, write down some value for them in some sort of PDB?
No, because the prediction for different types could be different. If you have a start state, let's say with type T0, and another state with the same type T0, the prediction for these two guys could be different, because you're actually exploring the state space below these two guys, and you might encounter different types below each one of them.
Even though the heuristic value is part of the type?
Even though the heuristic value is type of the, yeah.
Okay.
If you don't have invertible operators, did you consider using like a distance estimate to determine when to stop your forward probe? So not in bidirectional SS, but in regular SS, it seems like you could use the distance estimate, and then when it gets to 0, maybe that's a good time to stop.
You mean the heuristic for the nodes on the fringe or something?
Yeah, so like Jordan always uses the D function, where it's the number of steps along the path to the optimal solution instead of the heuristic, which is the cost.
Yeah, we didn't consider that.
So where do your types come from, and have you experimented with using how a different type will affect your performance?
Yeah, so the way we're building the types right now is we're using heuristic functions. And very often we get a node and we look for the heuristic function of this node. And the simplest scenario would be if you have two nodes of the same heuristic, with the same heuristic, they're going to be of the same type. But we also make some look-aheads in some cases. Let's say we look for the children, and then you see the distribution of heuristics for those guys. And then if you have another node with the same heuristic distribution, then they're going to be of the same type. If you have stronger heuristics, like more accurate heuristics, we expect to get better results. But all the experiments we run with simple heuristics. Like say, for this light tile puzzle, we're using Manhattan distance, or for block swirl, we're just using the number of blocks you have, out of place. And yeah, but it's definitely a very interesting question. Yeah.
So when you're working backwards from the goal, you'll only have a partial assignment to state variables because you'll only have the relevant variables, whereas when you're working forwards, you'll have a full assignment to state variables. Does that start to do weird things with your typing system when you've got have types of partial states and full states, and they've got to be somehow related to each other?
Yeah, so in the domains we worked, we actually have the full assignments for both forward and backward search. But I'm hopeful that whenever we apply to domains in which we're going to have full assignments for the forward search, but partial assignments for the backward search, there might be ways that you're going to compute the types for these guys, and on the type system level, on the type system space, we can still do this matching somehow. But I cannot tell it without trying, right? Yeah, you're just speculating.
So coming back to your initial example with my hypothetical construction company.
Right.
So if I'm preparing to bid for some contract, I run an estimate, the estimate says it's going to, and I know that if I run the estimate for an infinite amount of time, then it will be perfect, but I only have a couple of days to prepare it. Now it tells me it's going to be 2 weeks. So that sounds good, but if it turns out I can't actually meet that deadline, I'm probably going to pay a big penalty. So I would like to have some estimate in the confidence that you have in your estimate. Is that something that you can provide?
I can't provide that right now. That's a very interesting direction for research. And actually, we could do lots of very nice things if we had this kind of confidence. Like we could give bounds. Here's the prediction, but we know that, say, 95% probability is going to be within those bounds. Unfortunately, we don't have that right now. We only have the asymptotic guarantee that if you sample like a lot, eventually you're going to get to the perfect prediction. Yeah.
So it's a good thing I'm not in the construction business.
For now, yes.
So, do you have any idea of how your idea compares to just running an optimal planner for each problem?
So, if you want to run optimal planner for each problem, you probably want to stop at some point. One approach you could do is you run the optimal planner. Let's say you have your open list, and then you're going to get the best node you have in the open list. And that's also going to give you an estimate of the optimal solution cost. Running the optimal planning, it's just not an option, because like if you get for these very large state spaces, you're never going to get the optimal solution. So for instance, if you get this Lytel puzzle, we can get for the 5x5, but 6x6, it's just impossible right now. So the approach of running a little bit of, say, an A-star search and then getting some node in the open list and using that as an estimate, that might give you some good estimate for some domains, but I believe for most of the large domains, you're going to run out of memory before you have a decent estimate. More questions? Okay, thank you very much.